Actually, before we do that, in case I forget to mention it at the end, Monday is a holiday, so I won't see you until Tuesday. That means your homework now will be due on Monday, and so will your online test 7. Online test 7 will not include section 4.1. We'll get some of it done today, but not all of it. So I'll be keeping 4.1 till next week. Right? It'll be part A, homework 8, and that's fine. Of course, I will leave it open, in other words, visible in WebAssign, so that if you want to, and I suggest you should, maybe you should try and do some questions, because if you've got time to do them, it means less homework next week, right? So, but that's up to you totally, whether you want to or not. So, we are going to look at maximum and minimum values. And so, here is a nice boring curve, y equals f of x. And I'm going to call this guy, its x coordinate is A. This guy has an x coordinate of B. This guy has an x coordinate of C. And this guy over here has an x coordinate of D. And we are going to look at 2 types of maximums and minimums. There's a guy called an absolute maximum. And there's another guy called a local maximum. And then there's an absolute minimum. And then there is a local minimum. So there are actually 4, 2 of each. 2 types of maximums, 2 types of minimums. An absolute maximum would be here. And the absolute maximum is a point on the curve, right? So we're only talking about the curve from here to here, right? As a start and as a finish. Is there any point in the curve that's higher up, right? A bigger y value than any of the others? And that's called an absolute maximum. And we very often tell people where it is by just saying it happens at x equals d, or you might just say it happens at d, right? Now that's an absolute maximum. The other kind of maximum is called a local. And a local maximum is essentially any point on the graph where it reaches the top of a kind of hill, right? So you see how that's like at the top of a little baby hill? So local to that area, this is a maximum, right? That's called a local max. So there's an absolute max. You see that guy there? Isn't he bigger than anybody else higher up? And there's a local max. And kind of the same kind of idea. What do you think I'm going to call this guy at A? What do you think the name based on this choice? This guy's going to be called?
Absolute minimum?
Yes. And an absolute minimum is any point in the graph that is lower down than anybody else, right? It's got the smallest y value. In this case, that's clearly lower than anybody else. And it has an absolute minimum at A, or at x equals A if you prefer. And hopefully not too surprisingly, that guy there is called a local minimum. So to be a local minimum, you have to be at the bottom of a little valley, right? So at that point there, would you agree it's a kind of little dip in the curve? And we have described things like this. We like names for them. So if I say to you, oh, can you see that local maximum over here? You're kind of saying, oh yeah, I can see it, that hill there. I know what you're talking about, right? If I say the absolute maximum is 10, you can look at a function and say, oh yeah, the highest it goes is 10. In this case, we have got that. And I guess I should make everybody the same color. There we go. Are you comfortable about what a local and absolute max and min look like, right? Because so there are many different curves in the world, right? Many different graphs. And that means that there is quite a lot of different kinds of situations that can happen, right? So I'm going to try and show you by using the first 2 questions in the homework some of those variations on what we've talked about. So hopefully right now you are looking at question 1. Is that what you can see in front of you? Right. I'm going to make this as big as I can because, you know, seeing the graph is more important than anything else. Why is that answer still there? Stop doing that. I hate it when it does that. Brr. There. I think it's done. Right. Good. No answers now. So on this curve, there's a guy called A, B, C, D, R, and S, right? There's tons of different guys. In this guy, what is happening at C? My mouse is pointing at it. What would we call that bit at C? What's the name?
Local maximum.
Agreed. Now, it could have been an absolute maximum, but would you agree that this guy at the end at S is bigger than anybody else, right? You see the one at S, isn't that point higher up than anywhere else in the curve? So the absolute maximum would be at S. Have we all agreed that C is a local maximum, right? So I'm going to go here and put in a local maximum at C. So that's that covered. Right. Now back to the shape. What is happening at R? And be very careful here. What's happening at R?
Absolute minimum.
Correct. Isn't R the lowest part of that curve, right? Nothing goes lower down than at R. Now, here's an interesting thing. It is also a local minimum. So you can be both things at once. It's an absolute minimum and it's a local minimum. So that guy would be put in 2 different locations. What is happening at B?
Local minimum.
But just a local, right?
Mm-hmm.
And it's a bit of a trick question. What, if anything, is happening at A? Is it local, absolute, max, or min, or is just a normal point, nothing special going on here? What's happening at A?
Is it a local maximum?
It would be if the curve curved down the other side. But if you only get half the shape and then it stops, it doesn't count. To be a local, you have to go up and then down the other end. So it does look like it's going to curve, doesn't it? But you never see it curving, so you can't count it. So it's actually nothing, right? It's neither one or the other. And there's a guy boxed down at there where you put it in, right? So you put A in there. Right, here's our next one. Now this next one is, oh God, this next one is just horrible. Can I make this any bigger? Because there's, yeah. Whoa, go away. This is a piecewise salt. Oh God, this function's had a car accident, right? It's broken everywhere, right? There's bits missing. There's a lot of weird stuff going on here, and the naming might be a little bit out. So let me tell you the answers first. At X equals R, there is a local maximum. You agree it's the top of a hill. It's more like a top of a mountain, but it still counts. And isn't it also an absolute maximum? Because that's higher than anybody else. So at R, it's a local maximum and it's an absolute maximum. So far, so good. Could someone tell me what is happening at D? What name would we give to what's happening at D?
Local minimum.
What is happening, correct. What is happening at A?
Absolute minimum.
Right. What's happening at B? Nothing. No name to that. What's happening to C? No name for that. If I was going to give it a name, which we're not, wouldn't I call it a jump discontinuity? If I had to give it a name, but that's not the choice. So it belongs in that Neither thing, right? So do you see in this shape, you can be two things at once. Can't you be an absolute max and a local max? But can't you sometimes be just one, like an absolute max or just a local max? And some guys aren't anything, right? Some guys are just nothing special. You know, jump disc going to you is just a number, nothing going on here. Any questions about that, or you feel comfortable about what an absolute max and min and what a local max and min look like, right?
So S isn't going to be a local minimum because we don't have both sides.
S is not going to be a local minimum because we don't have both sides, correct? So if you have a curve that goes like that, even although your mind is telling you it's probably going to do that, if all you see is that, that guy is not a local minimum, right? To be a local minimum, it's got to do that. It can even do, you know, that, but it's got to do a both side thing, right?
Can it
Of
be
course.
a max local or not local
Absolute
minimum if it doesn't finish?
If it doesn't finish, it can be, but it doesn't guarantee it. And can you imagine a curve that looks something like this? Wouldn't that guy be an absolute minimum, right? But in a different world, couldn't we have a guy that looked like this? Wouldn't this be the absolute minimum? And wouldn't this guy be nothing at all? And we even give names to these. See the guy at the start and the guy at the finish? These guys, they're called end points. So end points can, but don't always have to be absolute max and mins. But don't end points can never be local max and mins because you don't get the other side. See, there's some little sophistications in there. Are we good with that? Okay. Just spend a few seconds here getting ready. The next question involves us doing a sketch of a function, and then from that function we've to write down where the absolute max and where the absolute mins are. So I'm going to show you how I would do it. You could do this in your calculator as well, but Desmos is just so much nicer, I think anyway. So the function that you're being asked to sketch is f of t, so I'm just going to call it y equals 5 cosine t. And can you see? That's what it looks like. And you're being asked to sketch it from -3/2 pi to +3/2 pi. So the way to make that is you do little curly brackets. You put in -3 pi for pi divided by 2. And then you do less than or equal to t less than or equal to 3 pi divided by 2, little curly bracket. Now, do you see what that does is it doesn't just let you sketch it. Do you see it actually allows you to only sketch the bit you're meant to look at? Now, this function has an absolute maximum. Tell me, you only need to tell me the t coordinate, right? In this case, it's the x coordinate, right? But it is the t coordinate as well. What is the x coordinate or t coordinate of the absolute maximum of this guy? Well, wouldn't it be there? Now, if I click on that guy, can you see the answer is 0? That makes sense? So the absolute maximum would be at t equals 0. Where's the local maximum? Look at that guy. Where is the local maximum?
0.
Say again, sorry.
Just 0 again.
Yeah, just 0 again. Right, you can be both. Let's see if we can try the other one. If I was asked to find a local minimum, wouldn't there be 2 places? Wouldn't it be there? So that would be at t equals pi. And wouldn't it be here? And wouldn't that be at t equals -pi? Would you agree those are local minimums? Are those guys also absolute minimums? What about those 2 points? Are they absolute minimums? Because they both get the same, right? They both are the same depth, right? They're both low. The answer is yes. So when you type in your answers, you put in pi, comma, and negative pi, right? You put in 2. Does this shape have any, excuse me. Oh, actually, I think I've answered that. Yes, we have. We're finished. There's nothing else to see here. Let's move back then. So if you are given a question, tell me about absolute max and absolute mins, but they only give you a formula. Wouldn't it be a good idea just to go to Desmos and sketch it? Because it's much easier to do it when you've got a picture in front of you than if you just look at the function. Now we're moving on to how to use calculus to find local minimums and local maximums. Right. Local minimums look like that, don't they? And local max look like this. And local mins look like this. If you give me a function, I could certainly plug it into the calculator, couldn't I? And just look at the picture and find where the local max and mins are. But there is a problem with that. Can you pretend that I had a function, I'll call it f of x equals ... And I sketched it, and it looked like this. And I'd say, oh, look, there's a local minimum, there's a local maximum. Hey, I've done them all. Well, let's pretend that I only did my x's from -10 to +10. Have I guaranteed to find every single hill and valley in that curve? No. Haven't I only told you what is a local max and min in this range? Theoretically, at least, couldn't this guy continue and then later on do a little curve? But I wouldn't, no. Well, I could always open my window. Well, you could, but even if you opened your window bigger, isn't there no guarantee that a little bit further on, it didn't curve? Right? And that's why you cannot do it with a calculator, because you don't know if you found all the answers. You only know that you found the ones that are in the window in front of you, right? The X's that you've decided to choose, but that's no guarantee that there's not others. So we're going to have to find another way to do this, and that's where calculus comes in. And we're going to use it to find local max and mins. So here is a term that we use. It's called critical numbers. Right. Critical numbers, CN for short, are the x coordinates of any point on a curve y equals f of x, where the derivative of x is 0 and or the derivative of x is undefined. And so the places where the local max and the local min live are here. And let's try and convince you why that's the only places you need to look. Why is the derivative 0 going to tell me where the local max is? Or why, if the derivative is undefined, is telling me where it could live? I should use the word could live, right? Because it might not be there, but at least that's the only places you need to look. If I draw a curve like that, right? Imagine that's part of my curve. Would you agree at this point here, the local minimum, isn't the slope of the tangent line 0? Does that make sense? At the bottom of a little valley, it's 0. What does that look like? Isn't that the derivative then is 0? at that point. Does that make sense why that's a good place to look? Look for when the derivative is 0. Suppose my curve looked like a V. Right? Good. Would you agree that at that one point there, isn't the derivative undefined? And that means that this guy is undefined. So what we are going to do is we're going to find where the local maximum and minimums are going to live by finding these guys called critical numbers. So we're going to find the derivative, and we're going to find out the values of x that make it 0 and the values of x that make it undefined. And those are the only places where local max and mins can live, right? There's no other way it can happen. And that way, I don't care where it happens, you know, the math will tell me, oh, by the way, at 2,000,001, there's a local max, right? Because that'll come out in the math. Of course, the chances that it's that big are pretty slim, but it could happen. So let's imagine that we had a function called g of x, and it is x squared, take away 6x plus 4. Do you recognize that as a quadratic? I'm just doing this to prove it works, right? I don't know what the quadratic, right? It looks like that, right? Step 1 in finding where the local max and mins will live, step 1 is to find the derivative. In this case, 2x take away 6. Step 2 is to find the critical numbers. So I am looking for when is the derivative 0 or when is the derivative undefined. Right, here's the formula or the function for my derivative. 2x take away 6. Would you agree that that's not going to have a problem, right? There's no place that's undefined. Would you agree? No problem with that. Okay. Now, I should be able to find out when it is equal to 0, right? There's the derivative. When is it 0? Well, you solve the equation, add 6 to both sides and divide, and there it is. There's my critical number. Can you see that at x equals 3, this guy has a 0 derivative. So at x equals 3, isn't this guy likely to have a local max or a local min, right? We are not going to be too detailed yet. We are just going to say, this is where you have to look. And then you can go and find out what it is. But isn't this the only place where it's going to happen, right? I know that there isn't any other place on this curve whose derivative is 0 or undefined. So there's only one place to look. And step 3, which we're not doing right now, is we check to see what is happening when x is 3. Couldn't I just plug that into Desmos and have a look and say, oh, it's a local min there, or oh, it's a local max there, right? I could do it that way. And you can also do it algebraically.
Are there cases where it's always going to be not a 0? For example, if the formula was x cubed, if it was a cubic formula, would I always just be able to say in my mind, oh, I know what kind of shape that is, and
There's going to be
therefore-
one max and one min, isn't there?
Yeah.
And that would pop out in step 3. But wouldn't you want to know where it happened, right? And calculus will tell you the x coordinate of where it would happen. Now let's do a cubic. It's a good question. Let's suppose I have a cubic x cubed, take away 9x. Right, that's a cubic. If I find its derivative, it's 3x squared, take away 9. I don't need to look for when it's undefined, but I do want to find the critical numbers. So I'm going to solve when is the derivative is 0, which in this case becomes when is that 0. If I add 9 to both sides, and then I divide both sides by 3, we get to there. What do you do to both sides to find x if x squared is 3?
Take the square root.
Correct. Should we do just a positive, or should it be positive or negative, and or negative?
Both.
Both. So I am making the prediction that this cubic has a local max and or min. I don't know which one goes where, right? At x equals root 3 and x equals negative root 3. Okay, well, let's put that to the test. I've got Desmos up here. I'm going to go into Desmos and I'm going to sketch that cubic and see if reality matches with what we believe. So it's y equals x cubed. Take away 9x. I may adjust my window a little bit. Let's adjust it. Let's adjust it over here. The y values look a little bit, well, I can make the x's small as well. I'm going to make it from negative 44. Looks like I probably need some more of the y value, so I'm hoping that negative 12 to 12 is enough, but I can tweak it if it's not. So very often you have to tweak things. Right, would you agree that's a pretty good picture of what the cubic looks like as far as we're interested? And would you agree it has a local max and min? And would you agree at that point about there? And the other one is down here. You see it? Do you notice that Desmos doesn't give you the exact answer? Doesn't it just tell you negative 1.732? I bet you the square root of 3 is 1.732 and some stuff. Right? So if you were doing a question like this and you thought, I don't want to do calculus, I'm just going to draw pictures all the time, aren't you going to be writing in decimals? And WebAssign's going to say you're wrong, I hope. I will say you're wrong anyway, because shouldn't you say the answer is square root of 3 and negative square root of 3? Because we want exact answers whenever it is possible. Have I convinced you that this actually works? Doesn't it find local max and mins? And it even finds them when the x coordinates are ugly, weird things like square root of 3s. So working on that same kind of vein, here we go. Let's show you another function which superficially, right, looks pretty harmless. I want to find the critical numbers for the function the cube root of x. So I need to differentiate it. So I'm going to call it a 1/3 power. Let's use that notation. No particular reason, just wanted to multiply by the power, reduce it by 1. Do some style points on it so the negative power becomes positive. Turn the fractional power into the cube root of x squared. Are we all happy with the derivative of this guy? Looks like that when you do style points on it, right? So the cube root of x has this guy. Now, I am wanting to find the critical numbers now. That is places where the derivative is 0 or places where the derivative is undefined. Let's start with the first one. When is the derivative equal to 0? And the answer is never. If you have a fraction and there's a 1 on the top and stuff on the bottom, that can never be 0. Because to be 0, don't you need a 0 on the top, right? 0 over 10, 0 over 20. So that's never going to happen. But I do have this one. There is a value of x where this calculation is undefined. Right, so that's going to be my critical number. What x coordinate, what x value can you put into this fraction and have a real hard time getting the answer? There's nothing to this question. That's a clue.
0.
Yes. Did you get my clue? Nothing to it. Oh God, you can tell it's Friday.
Yeah.
I feel like I'm in a dentist today. I'm telling you all my best material and it's gone. Picking on poor Alison and she had the bravery to answer the question. So anyway, here we go. You're right, 0. Now, what on earth is happening at 0? Because the cube root of function, the cube root function doesn't really have much going for it. Right? It's not a really messy looking function. I'm trying to find my Desmos. There we go. Well, I'm going to go into Desmos again and let's find out what's weird about the cube root of x. Here we go. Get rid of this guy. I don't know if Desmos can do a cube root. Let's find out. No, not really. Okay. So I'm going to do x to the power of a third. There. Isn't that the same as a cube root? I just don't have a cube root button. And I'm going to zoom in. Click off that. Whoa. Would you agree something weird is happening at the cube root? Right, you see right at 0, isn't something weird happening? But that is not a local max or a local min. Critical numbers only tell you where to look, right? The answer has to be here, here, and here. It doesn't mean that every single one of those 2, 3, or even 1 places has an answer, right? In other words, that something local max or min is happening there. It just means these are the places it could happen. Right? All dogs have 4 legs. Everything with 4 legs is not a dog. It doesn't work in both directions, right? All local max and mins are critical numbers. All critical numbers are not necessarily max or mins. You see, it works one way, but not the other. Right? Are we good with that idea that, you get critical numbers, but not all of them end up being max and mins? That's where the final stage, right, to check it. I'm doing checking right now by just sketching the thing and looking, right? But in the future, we'll show you other ways to do checks. How are we doing so far? Are you comfy with this? Find derivatives, find critical numbers, and then figure out whether it's a max, min, or just nothing, anything, going on at all. Well, that's that little piece done. How to calculate or to find local max and mins. Now we're going to do how to use calculus.
Quick question.
Yes.
If there's only one hill, as you say, does that mean that that is the local maximum and the absolute maximum always?
It would have to be. I'm thinking what you're saying. You're saying, suppose I have a shape and it only has one hill.
Mm-hmm.
Yeah. But the geometry of it, would you agree that it can't get any higher because it's only got one hill? Because if it had to get higher, wouldn't this guy somehow have to turn around to go up again? And the minute it turns around, wouldn't you have to have a minimum?
Yeah.
So yeah, I like your logic. That would make sense to me, that if there's only one local max, by definition, wouldn't that also be the absolute max? And if there's
Okay.
only one local min, the same thing would be true there.
Okay,
So-
thank you.
Now we're going to look at how to use calculus to find absolute max and mins. So I have some function and I would like to know its absolute max and min. A lot of these functions or these questions that we're going to do involve functions that you're given a start and finish value to. So here is my example of what that might look like. The question would be, find the absolute maximum and minimum value of this function in the range -1 to 2. So in other words, you can only use numbers from x equals -1 to x equals 2. Okay? Let's show you how you do it. Step 1. Find the derivative. Looking good? Now, in these questions, it's a good idea to do more than you normally would need to. That answer is technically okay, but aren't one of the rules of style points that we really haven't used much, factor the heck out of it? Remember that? That was like my second thing to do. So I am going to pull out 3 as a common factor. And now I'm going to give you the challenge. 1 minus x squared actually factors. And if it does, you should do it. What does 1 minus x squared factor into? One minus x squared. What are the 2 factors that make that?
1 minus x and 1 plus x.
Correct. Do you notice it's an ugly, weird looking difference of 2 squares? Right, it factors. Maybe the next time it's x squared minus 9. I think when it's that way around, people go x plus 3, x minus 3, right? That one's more familiar. But couldn't it be a quadratic, in which case x plus 2, x plus 7, right? Whatever it is, factor the heck out of it. Right, so make it look like the original, check. Factor the heck out of it, check. And only when it's a trig, see if there's a trig identity that will make it look pretty. So we'll hopefully keep away from the trig because they're horrible to do, but we can do them, right? And focus on those 2. So step 1 is that. Step 2 is we're going to find the critical numbers. Do you think that this derivative has any undefined values? Do you think there's a value of x that makes that undoable? No, agreed. Doesn't undefined tend to happen when you've got fractions, right? And the guy in the bottom 0, right? That's the kind of place where, 5 over x plus 1, that kind of look. But it does have places where the derivative is 0. But because we have already factored it, it makes solving this equation a lot easier than it would have been if I'd left it alone. If 2 things multiplied together give you 0, we call these things factors, then the math says that that has to be 0, or another possibility is the other factor has to be 0. In this case, x is -1. And in this case, well, you can do it any way you like. I'd just do that in my head. Would you agree x equals 1? So we have found our 2 critical numbers. That's what these guys are called. These are the x coordinates of where we should look. In fact, aren't these 2 steps the same 2 steps we did for local max and min? Right? But this is the new guy, step 3. This is different. complete the table of values. Now, in this table, we put in the x coordinate and we find what the f of x is, right? The y coordinate. And what are the numbers we've got? Well, we've got -1, oh, already there. We've got a 1, and we've got a 2. So your table will always start and finish with these two numbers. And then anything else in the middle has to come from here, right? So in this particular case, would you agree that both these critical numbers fit inside this window, right? Fit inside this range, right? -1 and 1 fit inside this range. I don't write -1 twice, right? Because it's there, but I do write 1. Can we pretend that it was 3 and -1, right? Can you imagine that that said x equals 3? If it was x equals 3, wouldn't our table be very small? There'd only be 2 numbers in it. Why wouldn't I use 3? Because it's not in this range. Does that make sense? You're only interested in what's happening between this value of x and that value of x. If any of your critical numbers are outside of this range, over here or over here, you basically put a little cross through them and ignore them. Now, I'm going back to the original function here. And if you plug in -1 here, what do you get? 3 lots in -1 is -3, add 1, that's -2. You plug 1 in here, you get 3, take away 1, that's 2. You plug in 2 here, you get 3 times 2 is 6, take away 8, you get -2, right? So you find the f of x, right, the y values that correspond to these guys. And now you're ready for the answer, step 4. There's going to be an absolute max, and there's going to be an absolute minimum. Okay, look at that table. What value of x do you get the biggest answer? Because the answer has to be in this table, nowhere else. What value of x do you get the biggest answer?
1. -1 or 1.
Okay, well, x equals 1, right? And isn't the maximum 2? So the absolute maximum value is 2. And it happens at x equals 1. Would you agree? The biggest answer is 2, right? So when we talk about the biggest answer, the biggest value, I'm talking about the value of f of x. And that's definitely the biggest. So that guy is my absolute max. What about these two guys? Would you agree that's a draw? Both of these then are the absolute minimums. And we know, well, depends on what you want. The absolute minimum of this function is -2. And it actually happens in 2 places. It happens at x equals -1, and it happens at x equals 2. But while I'm getting this set up, will you lot do your last name for attendance? And I'm going to go in and do a Zoom again for one last time. And we are going to verify that what we got from calculus actually matches reality, right? So you're doing your attendance while I'm getting myself set up here. Here we go. Right, let's get rid of that function. Our question was 3x, take away x cubed. A little curly bracket. We're only going to do it from -1 to 2. So -1 less than or equal to x less than or equal to 2. Finish with a little curly bracket. Click on the guy. Oh, that's a horrible scale. Where did that come from? There we go. Now, according to what we have in my table, the absolute maximum is here. Would you agree that happened at x equals 1 and its value is 2? And the absolute minimums happen at here. I can click on that a little bit better. Here. There we go. It was there a second, and then it disappeared. There we go. Isn't that its y value is -2, so its absolute minimum is -2, and that happened to x equals 2. And then there's another one over here. It also happened at -1. That's